All right, this is going to be a screencast for the post lab for Lab 3 Momentum. This is just, you might want to watch this to get a few ideas about some of the questions and make sure that you're doing everything you need to do as well as you possibly can and learn as much as you can on this lab, okay? So the mass of car 1, these, remember, are approximations. You're going to be close to this, but realize we may not have been using the same car or the same scale, and so there's going to be some differences. What I got for the mass of the original car, and I'm going to go ahead and do it this way. I'm not going to write on it because it seems to be having a problem, but I got with the writing right now. So, but I got 114 grams. And when you convert the 114 grams into kilograms, you're going to move the decimal 3 places to the left. So 1, 2, 3 places to the left, and that's going to give you 0.114 kilograms. And that's what we're going to be working with in our momentum calculation. The mass of car 2, remember, was actually the mass of the tennis ball, which is much lower, 56. And when you move the decimal 3 places to the left on that to convert it into current kilograms, you're going to get 0.056. All right. Now, those numbers you're going to use later, along with the length that the ball traveled. So, or excuse me, that the car traveled on the ramp. And my length that I got approximately was 75 centimeters. Now, you need to convert that into meters. So you're going to convert that 75 centimeters into meters, and that means you're going to divide by 100 or move the decimal 2 places to the left. When you do that, 0.75 meters. Now, these are the values. We're looking at meters per second as our velocity. So we're going to be dealing in this realm and not the centimeters. And when we get to momentum, it's going to be velocity, mass times velocity. And the mass is going to be dealing with kilograms. So that's why we'll be back up here with these numbers. Okay. All right. When you get your times, these are going to vary a little bit, but most people got approximately what I did. So you'd have like 1.23, 1.13, and 1.23. Now, if you had an outlier, one of these was like 1.6 or 1.7 seconds, probably a good idea to retry that one. And not use that in your data. To find the average, we're going to add these 3 numbers up and then divide by 3. And 1.20 is going to be the average time that it took for the ball or for the car to go down the ramp. And that moves us to our displacement. Now, displacement is different than distance. It is the length or distance in a given direction. So really, it mattered on which direction your car was going. So we found earlier that the car traveled 0.75 meters, and it traveled in a direction north, south, east, west, northwest, etc. So really, there needs to be meters north off to the side of this. I'm not going to worry about that on this lab because they didn't give you any space, but just be aware that that's there. And the time it took for that to happen was 1.20 seconds. From right up here, I use the average. When I do that calculation, when I divide meters or the displacement divided by the time, I'm going to be in meters per second, and that's going to give me my velocity. And when I do that, I get a number of 0.625 meters per second. And that makes sense, doesn't it? It's traveling about a little over half a meter in that time. So that makes sense. Now, to calculate the average momentum, I'm then going to take the mass of the car, which is in kilograms from the earlier page. So 0.114 is how many kilograms that car weighs. And the velocity I calculated was right above here, which was 0.625 meters per second. And when you do that calculation, it's a simple multiplication problem. You're going to get approximately 0.071 kilograms times meters per second. And that's a strange unit, but that is the unit for momentum. It's kilograms times meters per second because nothing cancels when you multiply those two together. Now, make a prediction about what will happen when the two collide. Make sure you talk about not only what the ball will do when it gets hit by the car, but also what is the car going to do once it hits the ball. Is the car going to come to a complete stop? Is it going to continue to move forward but slower? Is it going to bounce backwards? So be specific about what's going to happen to the ball and to the car. When you go through these calculations, they're going to be very similar to the ones you've done above. The thing to pay attention to, right, is make sure you're in the right units. When it's asking for meters, make sure you're looking at the meters. When they're talking about seconds, then meters per second, etc. Don't use grams instead of kilograms, that kind of mistake. You'll come through, and that will bring you to one of the overall basic questions at the end that you need to reflect on. And it says, explain how the momentum of car one changed as the mass was increased. And I think oftentimes this is a problem we would miss if you just said something like the momentum went up, or the momentum went down, or the momentum stayed the same. Be more specific. So talk about what happened in the lab. So give me some of those numbers that happened. So what happened when it was just the car, right? When it was just the car, you calculated the momentum to be what? And remember, the units for momentum are going to be kilograms times meters per second. And really, it needs a direction like north. But so what was the car when it was just the car? What was its momentum? What did you calculate it to be? What was the car plus 20 pennies, right? What was the momentum calculated to be? What was the car plus 40 pennies? And how much did it increase each time? So be specific on your values, and that will make sure you get all of the credit you can get on this problem. It says, what are some potential design considerations engineers should bear in mind when developing new cars? All right. So from the videos and the stuff that Matt Brumbelow talked about in the videos, think about some of those considerations that have to deal with things like speed, all right, velocity, momentum, acceleration, all those terms that we've been talking about. And how can you work those into an explanation of what considerations engineers need to be making when they develop new cars, especially being safer in collisions? Okay, good deal.